My name is Kendall Lam, and this is Lab 4 Circuits. So for an introduction to this lab, the purpose was to use an online circuit simulation to explore circuits with resistors in parallel and in series, use multimeters to measure current and potential difference, as well as study capacitors and their charging/discharging over time. Quick preview of the main results. The RC I found was 5.08 seconds, and the circuit behavior can be predicted using Ohm's law. Next are the main physics principles used. First one is charge conservation, which states that the charge is conserved in the circuit. Energy conservation, which states that the energy is conserved in the circuit. Node rule, which states that the current in equals current out at a certain junction. And loop rule, which is that the sum of the potential differences will equal 0 along any closed path in the circuit. Ohm's law was another thing we used, which states that the potential difference equals current times resistance. So for experiments, the first part was doing a prediction. We had two 1.5 volt batteries as well as two resistors connected in series, 47 and 100 ohm, and we predicted the current to be 0.02 amperes using Ohm's law. And reversing the ammeter, we got a negative value for the current, and when we swapped the ammeter for the voltmeter, the new current was 0 because the circuit was open, and the voltage is 3 volts, the same as the battery, which makes sense because there's no longer current flowing through the resistors. So for potential differences, we use the voltmeter and put the different ends at different points in the circuit in order to measure the potential difference, and they're all listed here. We can see that when we add them all up, we find that it's equal to 0, which makes sense with the loop rule, and we can see that the current is still equals 0.02 amperes after adding the voltmeter. And here is a quick graph showing how the potential difference is different across different positions of the circuit. So next, we explore the difference between voltmeter and ammeter and how they affect the circuit. So the voltmeter doesn't affect the current due to its very high resistance and is connected in parallel, so no current will flow through the voltmeter with a ideal voltmeter. And when connecting the ammeter in parallel, the current actually increased, and that's because the current flows to the ammeter instead of the 100 ohm resistor, because the ammeter has very, very low resistance. So for resistance calculations, we found the resistance of a bunch of different components using Ohm's law, and they were just calculated by rearranging it, and we can see that resistance 47 ohm resistor is 48, resistance of 100 ohm resistor equals 102, and the wire ammeter had no resistance as expected. These values are a little different, probably just because of the position of the ammeter. So for the next part, we explore RC circuits. For charging the capacitor, the bulb started bright, then got dimmer. The current decreased over time, and the same thing was observed for the discharging of the capacitor. When charging with the 10 ohm resistor, we got 15 seconds to charge and discharge. For the 20 ohm resistor, we got 27 seconds to charge and 26 seconds to discharge. So next, we did a quick graph using this formula right here. We graphed the natural log of delta V over delta V naught with and its relationship to time. So we got a slope that would be equal to negative 1 over RC. Our slope was negative 0.197, and all the data is shown here. And this is how we connected the 30 ohm light bulb, the 9 volt battery, which was used to charge the capacitor, and this is me discharging it, and calculating the voltage at the capacitor. So we found the RC to be 5.08 seconds based on the slope, and it should have been 6 seconds based on calculation of 30 ohms times 0.2 farads, but that's a 15.3% error. So for sources of error, we had an online circuit simulation, so we had ideal components. So most of the errors would be human errors, such as having trouble getting the potential difference across the capacitor data at the exact time. So what if you're doing this lab in real life and use an actual ammeter? Well, a real ammeter has low resistance, not zero, so we could expect that the current would go down. And what if we used a capacitor with no resistor in the circuit? If there's no resistor in real life, I mean, in the simulation, the capacitor would charge instantly. In real life, the wires have resistance, so it would probably take a little bit longer. So thank you for listening.